Almost 2 years ago, I published my first football AI video on this channel. Back then, I showed you how to detect and track ball players and referees on football pitch. I learned a lot in the meantime, so today we are taking this project to the next level. I'll show you how to use SigLIP embeddings to divide players into teams, how to use the Keypoint detection and Homography to create video game-style radar view. We'll also use the extracted data to calculate some advanced stats like ball trajectory and Voronoi diagram illustrating team control over the pitch. And most importantly, you don't need to be an AI guru to follow this tutorial. I'll guide you through the whole process. All you need to know is some Python basics. But before we start, let's get one thing straight. I'm from Europe, and where I live, we call this sport football. First thing first, let's lay out the plan. The project is quite complicated, so I've drawn a diagram illustrating all the models and tools we will use today. The raw video will be split into frames, and each frame will be processed by two models, Object Detector and Keypoint Detector. Both models will be fine-tuned on custom datasets. The object detection model will detect players, goalkeepers, referees, and the ball, while the Keypoint detection model will detect 32 characteristic points on football pitch. Since we'll know the positions of these points on both the video frame and the real pitch, we can later use them for perspective transformation. Detections for all classes except the ball will then be passed to ByteTrack, assigning each of them unique tracker ID and tracking their movement on subsequent video frames. Next, we'll use embedding analysis to divide the players into two teams. We will use SigLIP to generate embeddings, UMAP for dimensionality reduction, and K-means to create two clusters of players. Then, using previously obtained results of Keypoint detection, we'll perform perspective transformation in two directions, from pitch plane to frame plane, and from frame plane to pitch plane. The former will allow us to project virtual lines onto the video. The more accurate the predictions of our Keypoint detection model, the more closely the virtual lines will overlap with the actual lines on the pitch. On the other hand, by projecting the positions of ball and players from the frame onto the pitch, we'll be able to create a radar view known from video games showing the actual positions of players on the pitch. It should also be possible to draw the exact path of ball movement, as well as Voronoi diagram illustrating the control of individual teams over the pitch. Okay. Enough of the talking, let's write some code. Let's start by detecting ball, goalkeepers, players, and referees. To do this, we'll use YOLO V8 object detector trained on custom dataset. We have a dedicated tutorial on this channel showing how to train such models, so make sure to watch it if you want to learn more. This time, however, we'll focus primarily on aspects specific to analyzing football game. The original data for this project comes from DFL Bundesliga Data Shootout competition organized by Kaggle around 2 years ago. As part of this competition, the organizers released around 80 30-second videos from 20 different matches. Today we'll use this data to fine-tune our object detection and Keypoint detection models. I prepared a dataset of almost 400 images, which I uploaded to RoboFlow Universe. Each image has been annotated with classes ball, goalkeeper, player, and referee. Notice that goalkeepers and players are separate classes. This is because goalkeepers wear different colored uniforms than the outfield players. The additional information that a particular player is a goalkeeper will help us later when dividing players into teams. The original images, which has a resolution of 1920 by 1080, are then subjected to post-processing, including rescaling to a square format of 1280 by 1280. They're also stretched to fill the entire space. After the transformation, they look like this. Now, one of the key challenges ahead is reliable ball detection. The ball is a small, fast-moving object. It can be blurry in frames where it moves particularly fast, making it harder for the object detector to accurately locate it. Live sport events often have cluttered backgrounds, particularly in football, when the ball is high in the air amid spectators, not to mention other objects on the pitch that may look similar and confuse our model. When preparing a dataset, we need to make sure that all these anomalies are included. This will help to train a robust model capable of handling all these edge cases later on. Now that the dataset is prepared, it's time to train the model. By the way, all the models necessary for this tutorial are already trained and available publicly. So if you want to skip the training part and jump ahead, feel free to do so using the chapter timestamps. In RoboFlow Sports repository, you'll find a ready-made Google Colab template that we'll use for model training. Google Colab has a free tier allowing you to use GPU for a few hours. This should be just enough for us to train our model for free. Before we start, we need to make sure that the Secrets tab, located in the left sidebar of Google Colab's UI, contains our RoboFlow API key. We'll need it to download the detection dataset from RoboFlow Universe. To get it, log into your RoboFlow account or create one if you don't have it yet, and then expand the settings dropdown from the left panel and select API keys. Now copy it and paste in Google Colab's Secrets tab. Now we need to make sure that our environment is GPU accelerated. To do this, I run NVIDIA SMI command. If your output looks like mine, you are all set. If not, in the top bar, click Runtime and from Extended dropdown, select Change Runtime Type, choose NVIDIA T4, accept and restart the notebook. Next, it's time to install necessary Python dependencies. For the training of object detector, we only need two packages, Ultralytics to train the model and RoboFlow to download the dataset and deploy the fine-tuned model. This cell may take few seconds to complete, but when everything is ready, it's time to download the dataset. The link to the dataset is in the description below the video. Once you open it, click Dataset and then select the version you want to use. In my case, it's the latest one. Then click Download Dataset and in the Export pop-up, select YOLO V8 as the output format, checking Show Download Code. Click Continue and after a few seconds, a code snippet will be generated, which we copy and paste into Google Colab. We execute the cell and after a few seconds, the dataset will be downloaded to our coding environment. We can confirm that by opening the Data Explorer located in the left panel of Google Colab UI. In the datasets directory, we see football player detection dataset divided into test, train, and valid subdirectories. We can also view data YAML where, among other things, we can see class names and paths to the subdirectories. And finally, it's time to start the training. The most important thing here is to select a 1280 input resolution. By default, model trains with 640 input resolution. This means that every image and every video frame that runs through the model is first rescaled to 640 by 640 squares. In our case, this means that the amount of pixels in the input image is reduced by 4 to 5 times, and this is the problem because of our ball detection. You see on the raw image, the ball barely occupies few dozen pixels, and after such a rescaling, the amount of information in the image may no longer be sufficient to reliably detect the ball. For this reason, we increase the input resolution from 640 to 1280, pretty much keeping the amount of pixels the same and boosting the accuracy for ball class detection. But nothing in the world is free except of my tutorials, so we need to pay the price. And the price is slower training and slower inference. Since the input resolution increases the amount of memory needed during the training, we need to adjust our batch size accordingly. Batch size is the number of samples processed in one forward and backward pass of training algorithm. If you're training the model on more powerful GPU card, you might be able to use larger batch size. I set mine to 6. Training such a model will take at least an hour to complete, so I'll use the magic of cinema to speed up the process. By the way, on the right side of Collapse UI, you see few charts. One of them is GPU RAM, where 18 to 19 gigabytes of 22 available is already allocated. This is the value you need to keep in mind when choosing custom training hyperparameters. You see that we are already in red, just slightly larger batch size, and we would be done. Out of memory exception and training killed. When the training is finished, we can benchmark our model to make sure everything went well. A popular metric used in such situations is MAP, mean average precision. It measures the average precision across all classes and different IOU thresholds, providing a single number to represent the overall performance of the object detector. Here we can see the global MAP value and per class value. The model does quite well at detecting goalkeepers, players, and referees, and as expected, worse with ball class. But don't worry, we have few tricks up our sleeve that we'll use to clean up the ball detections. The last step is to upload the model to RoboFlow Universe. This way we don't have to worry about storing and versioning of our weights. We simply upload the training results to Universe and load the model when we need it. At the end, a link to RoboFlow Universe is displayed where we can find our uploaded model. Now it's time to use this fine-tuned model to build something cool. I debated for a long time whether to use regular IDE or Jupyter Notebook for coding in this tutorial, and in the end I chose Google Colab. It's just a lot easier to play with different visualizations, and I assume that a lot of viewers don't have GPUs, so it should be a lot easier for them to play with the code there. However, if you prefer to run your code locally, all the code, along with installation instructions, is in RoboFlow Sports repository. You can find the link to this repo and the Colab that I'm using in this tutorial in the description below. Okay, let's start with our Google Colab setup. Before we do anything else, we run NVIDIA SMI command to confirm that we have access to GPU. And after a few seconds, we should see the familiar output. If you see something like this, you're all set. Then we install our Python dependencies. This time I need 3 Python dependencies: gdown, Inference GPU, and Supervision. I use gdown to download files from Google Drive, Inference to pull and run models from RoboFlow Universe, and Supervision to process videos and, among other things, perform really nice visualizations. This installation should take a few seconds to complete. I sped it up just a little bit to save some time. Next, we install Sports repository. This is the repo where we store a big chunk of our sports demos and utilities. We'll use some of them for visualizing the outputs. And last but not least, we pull 5 files. Those are video files from the original Bundesliga Kaggle competition. And we will use those as our source videos for demos. So we already downloaded 4 of them. Here's the 5th one. And at the very end, I'm setting up an environment variable that will be consumed by the inference package, telling it which execution provider ONNX should use. So in that case, I would like to use CUDA. Our environment is ready. Now we can play with some models. Okay, so let's create a new text field and call this section ball players, goalkeepers, and referees detection. And now in the code field, we will import getModel from Inference package that we just downloaded and user data from google.colab. Now we will use users data get to extract the value of RoboFlow API key secret that we set up in Google Colab. You can see that beforehand I added this secret to Google Colab Secrets tab. Now I'm just retrieving it. And I'm also setting up another constant called player detection model ID. And I'm copying the ID of the model that we fine-tuned for RoboFlow Universe. The link to that page on RoboFlow Universe is in the description below. Now I'm creating an instance of model, calling the getModel function and providing my model ID and my RoboFlow API key as arguments. Let's just break the line because it's quite long and execute the cell. The cell may take a little bit of time to execute because we are pulling the weights from RoboFlow Universe and loading them into the memory. But I hope that in a few seconds we should be done. Yeah. Now I'll create another constant called source video path. And I will just set its value to one of to the path to one of the files that we downloaded from Google Drive just a few seconds ago. And I'm importing supervision as SV. The first utility that we will use from supervision is called get video frame generator. And we just pass the path to our source video file over here. And it allows us to loop over frames of the video. Here I'm just using the next to get the first frame from the generator, and I plot it on the screen. Awesome. Now it's time to run our model on that frame. So I'm calling player detection model infer, passing my frame and confidence threshold as arguments. And that function returns a list, so I'm just picking the first element from that list and then parsing the result into supervision detections. This is the class from supervision library that allows us to manipulate detections and visualize them and do all sorts of useful stuff. I'm initiating the most basic annotator from supervision called box annotator that draws boxes. And I'm creating a copy of the source frame, and I'm annotating that copy with my bounding boxes, passing the copy of the frame and detections to it. I run the frame, run the cell. Of course, I messed up. We need to pass the annotated frame to the plot image. Cool, we see the bounding boxes. Now, beforehand, I prepared a list of colors that I would like to use for visualization. So I'm just passing that list to color palette and passing that as an argument, running the cell once again, and the colors are updated. Awesome. Now it would be awesome to display more information about our detections. To do that, I'll use another of annotators from supervision library called label annotator. I'm passing the same list of colors. Those will be used as background for those labels, and I'm setting the text color for black. Now, below my box annotator, I will run the label annotator. So once again, I'm passing the annotated frame along with detections, and I press Shift Enter. Now what we see is the default label. It's just the class name. If I would like to show more information, I can do it as well. So I would like to show the class name and the confidence levels. So detections class that was created from parsing the inference results stores that information. So you can just get class names and confidences from there, use zip to loop over both of them at the same time and parse our labels. I just need to pass labels as another argument to label annotator, Shift Enter once again, and yep, we see both class names and confidence levels. Now let me show you how to go from processing of a single frame to processing of the whole video. First thing first, I define new constant called target video path, where I define the location of the result file. And of course, I would like our target file to have the same FPS and the same resolution as the source one. So to do it, I first create an instance of video info. This is one of the utilities available in the supervision that allows you to extract the information about the video. I pass the path to our source video file so that we extract the source information, and then I create another instance of another utility from supervision package called video sync that allows me to save videos to the hard drive. I pass the target location of the video and our video info object. This way we define the location and the FPS and the resolution. And then instead of getting just the first frame from our frame generator, we loop over the frames. Even important TQDM to get this nice loader visualization showing how many frames we already processed and how many frames are still to be processed. Then I indent all the code that previously was there to process a single frame to now process every frame in the for loop. I open the video sync with the with statement, and at the end of the nested for loop, I call video sync write frame to pass the currently processed frame into the video sync. Now I just run the cell. I speed up the footage so that we don't need to wait so long for it to finish processing. But when it's completed, we can download the result file. We just open the file explorer, quick download, and after a few seconds, the video should be on our hard drive. Here's the result. As expected, players, goalkeepers, ball, and referees are being detected. We see bounding boxes and labels with probabilities. So this is the most basic visualization of the results. Now let's try to do something more advanced. Our visualization so far was very simple and, to be honest, a little bit boring. So I plan to make it a little bit more interesting by using more advanced supervision annotators. To be precise, I will use ellipse annotator to annotate players, goalkeepers, and referees, and triangle annotator to annotate ball. Okay, so we go to the top of our cell and we start by defining new constant called ball ID. It will store the class ID for ball class. Now I'm renaming my ball annotator into ellipse annotator, and I'm no longer calling box annotator constructor. I'm calling ellipse annotator constructor. Below, I'm commenting out label annotator. We don't need it for now, but I'm initiating new one. Call it triangle annotator. And here I will use a nice yellow color to annotate the ball. I'm calling color from hex, and I'm passing the hex value of that yellow color. I can also define the geometry of that triangle. Those are in pixels. And now, just after parsing our detections, we will divide them into two groups. So the first group are only detections for a ball class, and the second group are all other detections. You can simply filter them out using class ID. So here we will have all classes but ball. Now I'm commenting out the labels parsing. And in the annotation section, I need to clean up a little bit. So I'm renaming my box annotator into ellipse annotator. And I'm passing different detections, those filtered out. And instead of calling label annotator, I'm calling triangle annotator. And here I'm passing only ball detections. Now, when I run the cell, we see new visualizations. Already looks a lot more interesting. The color coding is still the same, but instead of boxes, we have ellipses. And we have the triangle over the ball. But the triangle is quite close to the ball. Doesn't look so good. But Supervision have a utility that allows you to expound boxes by a specific number of pixels. So what we'll do is we'll expand boxes for ball class by 10 pixels, and that should move away the triangle marker a little bit higher. So when we run the cell, we see that the triangle is no longer touching the ball, it's just over the ball. That's a lot cooler. Now we remove one value from our color list, and that's because we no longer use the ellipse or previously box annotator to annotate the ball, and ball had class 0, so the first one in the list. And to adjust for that, we move all classes for remaining detections one down. So if players had class ID 2, now they have class ID 1. And on top of that, we use non-max suppression to remove overlapping detections. And we use class agnostic true to do it regardless of whether they are from the same class or not. It will just improve the quality of predictions. So here is our result after changed annotators. So I made it side by side. So on the left, of course, we see the initial annotations, and on the right, we see the new ones. I hope that you already see that I was aiming for this kind of video game vibe with ellipses below the players and this characteristic triangle marker over the ball. Now let's add some tracking. The next step is to add tracking. So for that step to have any sense, we need to have a way to display our tracker IDs, and we will uncomment label annotator to do it. We remove this extra color from the beginning of the color list, the one that we also removed from ellipse annotator, and we update text position from the default top left to the bottom center. So we want to display the text kind of like in the middle of those ellipses. Now we also initiate ByteTrack. This is the tracker supported by Supervision. And we will use it to track all detections but the ball. So we call tracker update with detections and pass all detections variable. But once again, this is the variable that stores all detections but the ball. Now we also uncomment the labels parsing. Instead of displaying class and confidence, now we will only display tracker ID and put this kind of like hashtag prefix in front of it. And we put back label annotator annotate call to our annotation section, pass our annotated frame, all detections, and our parsed labels. And when we run it, we see ellipses with tracker IDs. Awesome. So here's the video result for that step. We successfully managed to track goalkeepers, players, and referees. And with our next step, we are taking that to the next level, as we will divide players and goalkeepers into 2 teams. In theory, dividing players into teams is simple. We could, for instance, run our object detection model, crop boxes containing players, and then calculate the average color of pixels within the crop. However, this approach has few drawbacks. First, besides the player, the crop also includes the background, like the grass, the stands, or even other players. Second, the proportion of pixels representing the player and the background in the crop varies depending on player's pose. Third, different lighting in different areas of pitch affect the average color value. All this makes the color-based approach unreliable. It may work for some scenes, but it will definitely fail for others. Therefore, I've decided to use an approach that might seem over-engineered, but works perfectly in practice. Some time ago on this channel, I showed you how to use SigLIP image embeddings to look for similar images. Today, we'll use a similar strategy to look for players from the same teams. Embeddings capture a semantic meaning of an image, making it robust to variation in pose, occlusions, and lighting conditions. This time, instead of SigLIP, we'll use SigLIP. It's more computationally efficient, making it a better choice for real-time applications. For each crop containing a player, we'll generate a 768-dimensional SigLIP embedding vector. Then using UMAP, we'll project this vector down to 3-dimensional space. UMAP is a dimensionality reduction technique that helps us visualize high-dimensional data in low-dimensional space while preserving the relationships between data points. Finally, we'll try k-means to divide players into two teams. K-means is a clustering algorithm that helps group similar data points together. It will find two clusters in our 3-dimensional embeddings representing the two teams. Trust me, it sounds complicated, but it's actually quite simple. So, first thing first, we need to collect a sufficient set of player crops for us to use to train our team classification model. To do it, we once again create an instance of frame generator, but this time, instead of looping over every frame, what we will do is we will use stride argument to skip every 29 frames and return every 30 frames. Just like before, we will use a for loop to loop over frames in frame generator. We will use QDM to get the nice loader and maybe add a description saying that we are collecting crops. I also created a list called crops before the for loop, and we will append our crops to that list. Now inside the for loop, I'm doing everything that we already done in the previous sections. So I'm calling the infer function in our player detection model, pass the frame, pass the confidence threshold, extract the first value from the list, and parse that result into supervision detections. Then once again, I'm running non-max suppression to remove the overlapping detections, setting the IOU threshold to 0.5, once again making it class agnostic. Next, we'll filter our detections by class. So previously we already done that for ball class, but now we will do that for players. So in our model, player have ID 2, so we just use that player ID to filter detections by class ID. And now what we do is we do least comprehension to loop over detections, the player detections that we already have, and use one of the utilities from supervision package that allows us to crop out parts of the image based on the box definition. So I execute that cell just to make sure that everything works correctly. The FPS of that video is 25, and we are striding every 30 frames. So that's up to 750 frames. So far so good. Looks like we get all the frames. To make it a little bit easier for us to use that, I wrap all that code into a utility function called extract crops. Now I just update the parameter in the frame generator so that we don't use the global value and we use the value that is passed as the argument to extract crops function. And below we can test if it still works. It should. So let's just wait a few seconds for it to finish. Yep. Now we can just display the count of our crops. So altogether we got 478 crops. We can plot sample of that set, let's say 100 of them, just to visually confirm that we have everything we want. And here's the result of crop collection. So we see that there are players from green and red team. Now we need to build an algorithm to automatically sort them into those two teams. So I prepared a code snippet that will allow us to load SigLIP model that we'll use to create embeddings for those crops. The code is pulling SigLIP from Hugging Face and loading it into the memory, and also making sure to load the model on the GPU if the GPU is available. And now we need to run this model on those crops and get our embeddings. So the first thing that we need to do is to convert our crops from OpenCV format that we have right now into the pillow format. So Supervision is using OpenCV as the engine internally, and SigLIP is expecting those crops to be in pillow. So we use least comprehension to convert crops from NumPy arrays into pillow images. Now we also use chunked function from More Iter's tools package to split those crops into batches. So I set the batch size to be 32. I pass our crops and the batch size to chunked function, and as a result I will get batches. I initiated the list called data where we'll store our embeddings. Now we just loop over the batches, use TQDM to get the nice loader showing us how many batches were already processed. And if you ever use transformers package, you know that models there usually have the model and the processor. And the processor is responsible for pre and post processing the data, and the model just executes. So here we pass our batch to preprocessor that creates inputs in the format expected by the model. Then we just pass those inputs into the model, get our outputs. And then what we need to do is from those outputs, get our embeddings. So embeddings are located in the last hidden state, but that layer have higher dimension. So it's not 1 by 768, it's more than that. So what we need to do is we just average out across the second dimension so that in the end we will get those nice vectors. And when everything is done, I just append those embeddings into the data and use NumPy array. The model was running in the training mode, so it was calculating the gradients, and that's why we got that exception. So we will just call with torch no grad and indent everything inside that. And this will make sure that the model don't calculate gradients. We need to restart the upper cell that extract the crops because we already overrode the crops from OpenCV to pillow, and right now you would get an exception here. So we need to restart the upper cell and go back here. We already have the crops. We calculate embeddings. So every batch was 32 by 768, and when we concatenated them, we got 478 by 768. So that means that we have 478 examples that exist in this very high dimensional space with 768 dimensions. And that's very hard to imagine, of course. So we will use UMAP to reduce those dimensions. And in the end, we'll get 478 examples in three-dimensional space. And when we'll have that, we will just pass those examples into this like very popular and basic clustering algorithm called K-means that allows us to predefine the amount of clusters. Of course, we talk about football, we have two teams, so we have two clusters. So for now, we initiate both the UMAP reducer and the clustering model. And once that is completed, we will use the UMAP to reduce the amount of dimensions. So we just call fit transform method. That method is doing exactly what you think it's doing. So first it trains UMAP, and then once it's completed, it also run kind of like the inference, the projection on the input data. And as expected, we got 478 by 3. Now we take those projections and we pass them into the clustering model, this time calling the method fit predict. This one will first train the clustering model and then run the predictions. And now we can take a look at the sample of that data. So it returns as either ones or zeros, depending on, so this is pretty much the label of the cluster. So we can treat it as class IDs, for example. Now we can easily filter out crops based on that team ID. So I just zip over the crops and clusters, and when the cluster is equal 0, I keep them and store them into the team 0 list. Now when we display that list, so we display those crops similarly as we did before, we will see that we'll only have players from one team. So this is how the result looks like. We successfully divided players into two teams. Here is the red team. Now we need to plug in our team classification code into our tracking demo. So instead of using the code that we just wrote, I will import team classifier from a sports repository. Like internally, that class is exactly what we just did. I just showed you what is inside, but it's a lot easier to use it instead of our code, because I don't need to run every step manually. I can just run it all nicely packed into the team classifier. So at the very top of our tracking code, I call extract crops, pass the path to our source video file, and then pass those crops to our team classifier. So all that will happen before we even start tracking. This way we will have the model trained and ready to use when we want to process frames. Now, what we need to do next is we need to divide our all detections. This is the object that we created a few minutes ago. It stores all detections except the ball. And from that group of detections, we cut out even smaller portion, those that are only the players. And what we do next is we do exactly what we did before. So we convert the crops, we crop out those detections from the whole frame, and then pass those crops to our team classifier, to the predict method. And as a result, we will get team IDs. We assign those team IDs to class IDs. So when we run our annotators, it will automatically pick the color encoding from the one that we had so far. So previously it colored goalkeepers with blue and players with pink. And now when we run it, that color encoding is now converted into teams. So we have pink team and blue team. But we don't have the goalkeepers. Goalkeepers are still not assigned to the team. So how do we do that? To do it, we will need to write a short heuristic. The assumption is pretty much that if we take the positions of all players from both teams and we will average those positions out, we'll have kind of like the centroids of both teams. And goalkeeper should be closer to its own team's centroid. So the assumption is pretty much that the defending team is closer on average to their goalkeeper than the attacking team. On average, because individual players, for example, could be closer, but the average of the team should be exactly how I described it. So we will calculate this inside this helper function called resolve goalkeeper's team ID. This function will take player detections and goalkeeper detections. So remember, our player detections already have class ID where that class ID express the team ID. So players have either 0 and 1 depending on the team that they are belonging to, and goalkeepers for now have the regular class ID, something that does not relate to their team. Now we need to convert boxes into points. So to be able to calculate the average position of the player, we cannot have boxes. We need to have some exact location of that player. And what we will do is we will convert those boxes into a single point that is in the middle of the bottom edge of the bounding box. Supervision has a utility that allows you to do it very efficiently. So now we have two NumPy arrays, goalkeepers XY and players XY. And those NumPy arrays store coordinates of both goalkeepers and players. So next, what we will do is we will calculate the centroids of both teams. So we filter out players based on their class ID. Like I just told you, class ID right now express the team ID. And when we do it, so filter out the NumPy arrays based on that condition and then calculate the mean, we end up with the average XY coordinate of the team. And to wrap it up, we just loop over the goalkeepers because it's quite possible that on a single wide angle frame we have more than one goalkeeper. So we loop over the goalkeepers, we calculate the distance from the goalkeeper to centroid of team 0 and centroid of team 1. And then what we do is we just append a value to goalkeeper's team ID list. And we just do an if statement. If the team 0 is closer, then it's 0. If team 1 is closer, then it's 1. And at the end, we convert that list into NumPy array because our class IDs, and we will once again use class ID to store information about the team, is a NumPy array. So we need to return the NumPy array. So the utility is ready. We just go back to our code and call that function, passing the goalkeeper's detections and player detections, and the result of this function will be saved to goalkeeper's detections class ID. Now what we can do is we can take the player's detections and goalkeeper detections and kind of like merge them together into a single detections object. And then we will use that object to pass into our annotators and visualize them. So the idea is that right now also goalkeeper should have the color of the team assigned to it. So we need to put all detections back instead of player detections in all of those annotators. And once we are ready, we can run the cell. So of course, once again, it will collect the crops. It will train the team classifier, so all of that will take a little bit of time. But it should be almost there. The merge function in detections object takes a list, and we passed players detections and goalkeepers detections individually, so we just need to wrap those values in the list and pass them as a single list instead of individual objects. So we restart the cell once again, and in just a few seconds we should get the visualization. Yeah, so the goalkeeper is the most left player on that frame, and it looks it got assigned to a pink team, which just by looking at the frame seems correct. We don't have the referees visualized yet because they are not part of the all detections anymore. So what we will be doing is we just add one more filtering statement. This time we filter by referee ID, and we add those referee detections to our all objects after we assign teams to players and goalkeepers. So now we just have a list of 3 elements instead of list of 2 elements. So we run the cell once again, and after a few seconds we should see both teams and referees on the frame. Awesome. And here's the result when we run it for entire video. Works really well. There are, I believe, no accidental team swaps. The only moments where we lose somebody is when it gets occluded and it's no longer detected at all. So yeah, really robust solution. Before diving into keypoints detection, let's take a quick detour to understand homography. Homography is a mathematical transformation that maps points from one plane to another. When taking a picture of flat surface, like a football field, from an angle, it will be distorted due to perspective. The further away something is, the smaller it appears. Homography allows us to undo this distortion and get a bird's eye view. This is critical for our football AI because it enables us to accurately track player positions, ball movement, and other key events, regardless of where the camera is positioned and how it's moving. To perform this transformation, we need to calculate a homography matrix. This 3x3 matrix encapsulates the geometric relationship between the 2 planes. It is computed using corresponding sets of points in both the original image, the camera perspective, and the desired top-down view. Typically, we need at least 4 such point pairs to solve for homography matrix. Once we have the matrix, we can apply it to any point in the original image to find its corresponding location in top-down view. When the camera is static, using homography for perspective transformation is simple. We determine the position of corresponding pairs of points on source and target planes once, and since the camera doesn't move, we can apply the same homography matrix for each video frame. We even showed this approach in our vehicle speed calculation tutorial. Cameras at sport events, however, are often placed in various locations and angles and frequently pan, tilt, and zoom during the game. This dynamic nature makes it challenging to determine the position of corresponding points between the video frame and real world. To overcome this challenge, we'll train YOLO V8 keypoint detection model to automatically identify specific characteristic points on football field. Keypoint detection is a computer vision task that involves identifying specific points of interest in image or video. Keypoints represent distinct features or landmarks, such as facial features, body joints, or object corners. In our case, we'll use keypoint detection to detect characteristic points on the football pitch. Since the camera can pan and zoom in and out freely following the action, we rarely see the entire field. Therefore, we need to define our points densely enough so that at any time, even when the camera is tightly following the action, at least 4 characteristic points are visible. This requirement is related to homography. We need at least 4 reference points to run it. I defined 32 characteristic points on the pitch, including corners, penalty areas, goal areas, penalty spots, and the center circle. Labeling these images took forever to complete, so if you appreciate the effort and would like to see more AI projects like this, make sure to subscribe and leave a like. It motivates me to keep going. Now back to the video. Once the labeling was completed, I applied post-processing steps where we rescaled each image to 640 by 640 squares by stretching them to new format. I trained over 10 versions of this model, and in my tests, stretching the frames performed far better than maintaining the original aspect ratio and using Letterbox. Speaking of model training, let me quickly show you how to do it. Once again, I remind you that all models used in this tutorial have been already trained and are available publicly on RoboFlow Universe. So if you want to skip this section, feel free to do that using chapter timestamps. However, if you never trained Keypoint detection model before, I highly encourage you to stick around. In the RoboFlow Sports repository, you can find a link to Pitch Keypoint Detection Model Training Google Colab. So if you want to reproduce my experiment or port this demo to another sport or a completely different use case, you're all set. The notebook starts with standard environment preparation. Before we start, we need to add RoboFlow API key to Google Colab's Secrets tab. It will be necessary to download the Pitch Keypoint Detection dataset from RoboFlow Universe. Next, let's make sure our Google Colab is GPU accelerated. To do this, I run NVIDIA SMI command. By default, my notebook runs on NVIDIA T4, but due to the large amount of computation required to optimize the model, I'll upgrade my GPU to NVIDIA A100. I click Runtime and then select Change Runtime Type from the dropdown. When the pop-up appears, select A100 and click Save. This GPU is available only for Colab Pro users. Still, you should be fine with NVIDIA T4. It will just take a lot more time to complete the training. Next, we install the necessary Python dependencies. Similar to object detection model training, we only need 2 packages, Ultralytics and RoboFlow. Once the installation is complete, we can proceed to download the dataset. In RoboFlow Universe, we select the desired dataset version and then click Download Dataset button. When the pop-up appears, select YOLO V8 as data export format and check Show Download Code. After clicking Continue, we see a code snippet that we can simply copy to Google Colab. We paste it, press Shift-Enter to run the cell. When the download is complete, our data should be visible in Datasets directory. We can confirm this by opening the Data Explorer in left sidebar. The football player detection dataset is divided into 3 subdirectories, and each of them in typical YOLO style contains another directories, images, and labels. When we open DataYAML, we can see something new, however. It contains a flip index section where corresponding pairs of keypoint indices are defined, indicating which keypoints should be swapped when an image is flipped horizontally. This information will be used when creating horizontal flip augmentations. Once we have the data, we can start the training. I'll be training YOLO V8 Expose for 500 epochs. And I know what you're thinking, 500 epochs? Like, do we really need that? Here's a small example where keypoint detection results are marked in pink and the lines projected using homography are in blue. We will build this literally in a few minutes, but in the meantime, we can see how the projected lines no longer closely overlap with the lines on the actual football pitch, all due to minor key point detection errors. That's why we need to train a bit longer and optimize our model as much as possible. To speed up the process, I set my batch size to 48. I remind you that I'm running my training on NVIDIA A100. If you don't have access to such a beast, you'll need to adjust this value accordingly to the amount of VRAM you have. Also, make sure to disable mosaic augmentations. Mosaic augmentations combine multiple images into one during the training, increasing the diversity of your training data. Those augmentations work great when you expect multiple objects in various configurations to appear in the image. In our case, there's always one object in the frame, the peach. In my test, I noticed that mosaic augmentations sometimes misled our model, making it expect multiple peaches on one frame. You can disable this feature by setting the probability of mosaic augmentations to 0%. Training this model, even on NVIDIA A100, takes a lot of time, so see you in a few hours. Just kidding. Let's use the magic of cinema to speed up the process once again. After the training, let's see how the model performs on some images from validation dataset. It looks promising. Regardless of perspective, the model provides good quality predictions, except of one outlier on the third image from the left in the top row. The pink dot seems to be in a rather random place. We'll see how the model handles images from our test videos. Finally, I upload my model to RoboFlow Universe. I can now easily deploy it in browser through the RoboFlow API and locally using the Inference package. Let's plug it into our football AI demo. Okay, so let's start by creating another text cell and call this section Peach Keypoint Detection. Similarly as before, we copy the ID of our model from RoboFlow Universe. So we previously did that for object detection model. Now we do it for peach detection model. We create a constant and assign the copied value to that constant, and then call the getModel function that we imported from Inference at the very beginning of that tutorial. Pass our RoboFlow API key along with the model ID. Press Shift Enter, and that should download the model from RoboFlow Universe and load it into the memory. We didn't need to extract the RoboFlow API key from secret stub because we did it already. So we just had that value all the time in the memory. So now we do exactly what we did before for object detection, but now we do it for keypoint detection. So we create frame generator. Once again, we extract the first frame from that frame generator and display that frame on the screen. And now we run the infer method of our peach detection model, pass the frame and confidence threshold, and parse it, this time not into the detections object from supervision, but into keypoints object from supervision. And once we do that, we have access to a whole array of annotators dedicated for keypoint detection. One of those annotators is a vertex annotator. This one is pretty much using simple dots to visualize all the anchors of the skeleton. So we just set the color and the radius, and exactly like we did before, we copied the frame, assign that copy to new variable, and then run vertex annotator annotate, passing that annotated frame, which is the copy of original frame, and our keypoints objects to it. And we run that. and just like before, I forgot to swap the variables in exactly the same place. So here's the result. And what we can notice immediately is that there are some key points that are in the right place, and there are some key points that are kind of like randomly located. So just like object detection results, key points also have confidence, and that confidence can be on the skeleton level and on the anchor level. So when we take a look at the result, specifically at the confidence values, we see that there are some anchors that have very low confidence. We can filter those out. So I just set out the threshold for anchor confidence at around 0.5. And now I will use that filter to remove key points that have lower values. So I just pick the first skeleton from XY, filter anchors from that skeleton based on that confidence threshold, and then I create new key points object, call it frame reference key points, and assign those filtered out key points positions to that new object. I call it frame reference key points because I prepare already for the homography, so we'll have frame reference key points and pitch reference key points, and we'll use them to transform perspective later on. So here are the filter out anchors. Those look really well. They are almost exactly in the places that we would expect them to be. And here is the result for the entire video. What is also important that the anchors are stable. If the model is undertrained, they tend to vibrate and jump from one place to another. It happens from time to time, but it's very subtle, and we'll be able to work with that result in the next stage. So as we discussed, to perform homography, we need to have pair of points that exist both in source and target planes. So we already have points on a source plane because those are the points that we acquire using key point detection. Now let me show you points on the target plane. So inside a sports repository, we have an object called soccer pitch configuration, and that class stores information about coordinates of our 32 points on a real football pitch. So when we print out config vertices, we see that we have a list with 32 values. Those values are tuples and describe the coordinates in centimeters of all 32 points. We also have something called edges, and those describe which vertex is connected to which vertex. On top of that, in the sports repo, we also have annotators. We will use few of them today, but the simplest one is draw pitch. So we can pretty much print out the layout of the pitch based on the configuration that we pass. So let's do that. Let's display that result in the collab. Now we have everything we need to transform perspective, except of the actual code that will do it. So let's write a quick utility that will perform that transformation. So I'll call that class view transformer, and it will take source points and target points into the constructor. Inside the constructor, we need to make sure that those points that are stored in NumPy arrays are in float 32 format. So I'm just running as type on both the source and target. And then I'm creating a field called M, and that will be our homography metrics. We'll calculate that homography metrics using OpenCV method called find homography. This is the method that allows us to pass more than 4 points to calculate the homography. We do it because when we will run our code, we will have sometimes more, sometimes less points visible on the frame. As we already said, we need at least 4, but we would like to be able to have more than 4, and that method allows us to do it. So find homography will calculate our homography matrix, and then inside transform points, we'll use that homography matrix to move our points from one plane to another. Because homography matrix is 3x3 matrix, we need to expand the dimensionality of our points, because our points only exist on 2D plane. So we reshape that NumPy array storing points so that it will have 3 dimensions. Then we will run perspective transformation with those points with expanded dimensions and our homography matrix. And then once the point transformation is completed, we will remove that one extra dimension. So now I just copied our keypoints example that we already wrote, and we will add a transformation to that example. So what we will do is we will first of all, have a transformation from pitch to camera perspective. So we will take all the points we have, and we also have edges, as we just explored. So we will transform those points and edges from the pitch perspective to the camera perspective. So to visualize those edges, we will use edge annotator, that is also part of supervision library, and now we will perform the point transformation. So we already have a frame reference key points. As I told you, it was part of the preparation for that transformation right now. And now we convert our config vertices first into NumPy array, and then we filter them using the same filter as we filtered to remove the redundant key points from the key point detection result. So the idea here is that we have out of the box, we have 32 key points, and then we remove some of them because they are not visible on the frame. And we would like to remove the same key points from frame perspective and from pitch perspective so that we end up with pair of points that exist on both planes, and then pass those points into transformer view transformer to perform that transformation. So once we do it, then we take all the points that exist on the pitch plane and we'll transform them to the camera view. This way we'll be able to draw points that don't even exist there, but most importantly, we'll be able to draw the lines connecting the points that exist on the plane and that don't exist on the plane because they are not visible. So I'm just doing a little bit of NumPy magic here to have the same shape that is expected by keypoints object in supervision. And then I call edge annotator annotate method, passing the annotated frame and my frame all key points, and as a result we get a nice visualization where the pink points are the detections coming from our key points detection algorithm, and the blue points and the lines are the projections performed using our view transformer. Now let's go ahead and perform a transformation in the other direction. So let's transform points from a camera view into the pitch perspective. So to do it, I went ahead and I copied our detection code that we wrote a few minutes ago. I'm removing from it the part that was responsible for visualizing the results on camera frame. But I'm adding code that is responsible for key point detections. So at this point, I have the code that is a mix of our object detection example and key points detection example. And the idea is that we take our detections that we acquire using the object detection model and move them to pitch perspective using our view transformer. So first thing first, we acquire the position of ball on the frame. And we do it the same way as we did it with goalkeepers and players a few minutes ago. So we call get anchor coordinates, and we pass bottom center as the desired anchor. So once again, this utility converts boxes into points, and we pick the point on the bounding box that we are interested in, and we chose the middle of the bottom edge of the bounding box. Now we import draw pitch annotator, the one that we used already a few minutes ago, and draw points on pitch annotator. So the draw pitch annotator will draw the entire layout of the football pitch, and draw points on pitch will allow us to visualize the position of projected object on the pitch. So first thing first, we call the draw pitch annotator, pass the config. This will result in visualizing the layout of the football pitch, and then we call draw points on pitch, pass the config once again, but most importantly pass pitch ball XY. So this is the projected position of the ball that is already processed by view transformer. And now I'm just passing color configuration, radius configuration, so just a few things that will impact how the position will be visualized, and I'm just calling plot image, passing the pitch, and we will see the result in just a second. Because it's the same example that we copied from a few minutes ago, it also collects the crops and calculate embeddings, so that will take a little bit of time before we will see the result, but it should be, yeah, it's exactly what we expected. We see the ball near the edge of the football field. So we have the ball already projected. Now let's project players. So I just copy those two lines that I previously used to project the ball position, and now I take player detections, acquire bottom center positions for all the players, and I transform them from camera perspective to pitch perspective. And I also paste those two lines once again, this time to project the position of referees. So right now we have three variables. We have pitch ball XY, we have pitch players XY, and we have pitch referees XY. And just to remind you, in the pitch player XY, we already have both the players and the goalkeepers. And now I just copy and paste the draw points on pitch call to visualize both players and referees. And because we would like to visualize players from both teams with different colors, then that's exactly what I do. I filter out pitch players XY based on the class ID of the player. As you remember, we use class ID to store information about the team ID. And then I visualize both of those teams with different colors. And finally, I visualize also the position of referees. Here we don't need to do any filtering. We just pass a different color, and that's it. And when we run it, we should see a visualization with players with from both teams, because we will run a team assignment, as well as referees and the ball projected on the pitch. So we just need to wait a few seconds for that training to complete. And once that happens, we should see the visualization, and there it is. Awesome. Here's the all-around result. I put both the pitch visualization and the frame visualizations all together, so that we can see how the ball is moving on both visualizations at the same time, and players are moving from one side of the pitch to another. Yeah, it looks really well. Now we can easily convert this radar visualization into Voronoi diagram that express the control of the team over portions of the field. So to do it, we just comment out the visualization that we just created, and we use draw pitch Voronoi diagram function, available in supervision just as well. And it will be actually a lot easier to make that visualization. So all we do is we pass the config, of course, and then we pass teams as separate arguments. So we have team 1 and team 2. So to do it, we do exactly what we did above. We filter out pitch players XY coordinate based on class ID values. Then we pass information about the expected color configuration. So we use the same colors as we did above. So different color for team 1 and for team 2. And we're almost there. And finally, we pass the pitch that we generated above. And once we run it, of course, as usual, we need to wait for the team classification model to finish training. We should see the generated Voronoi diagram for our soccer field. It's taking a little bit of time to complete. Stay patient, yeah, and there it is. And finally, I put together pretty much the same visualization that I did before for the radar visualization, but this time with Voronoi diagram, updating accordingly to position of players on the pitch. Yeah, I mean, it's kind of mesmerizing to look at that result both at the same time. This video is a lot longer than I initially anticipated, but there is one more item on our to-do list that I promised you that we'll explore, and this is ball trajectory analysis. So I keep my promises, but instead of me coding that piece in front of you, we'll just go through the code that I already written, and I will just explain it step by step. So here is our ball trajectory analysis code. It's actually quite simple because we have almost everything we need. We detect ball using our player detection model. We detect field key points using our key points detection model, and then we perform a perspective transformation. That's all we did so far. But to make those results a little bit more stable, I created a queue where I store my homography matrices for a time window equal to 5, and I average out values in my homography matrix, and I put it back to a view transformer. This way, when we have those small vibrations of key points, we can mitigate that problem by just averaging out the values in the homography matrix. And then I just put values that I transformed from one plane to another inside the list. And that list stores coordinates of the ball on the football field. And most of the time, we only have one ball, and that's great. But sometimes we have none. And even better, sometimes, very rarely, but sometimes we have more than one ball. So now what we need to do is we need to clean up those results. So what I'm doing is, first of all, I just remove all the entries where I have more than one ball. I just assume that if I have more than one ball, I don't know which one is it, so I just remove all of them. In reality, it would be possible to figure out which ball is the right one, but turned out I don't really need to do it. That don't happen very often, so I don't lose a lot of data this way. Next, I just visualize the path that I got. And here is the small problem that we have. So most of the time we get the correct path, but sometimes we don't. So sometimes we get those spikes, and that's because the one ball that we actually detected was not the correct ball. So those are those frames where we didn't detect the right ball, but we detected the wrong ball, and it's still in the data. So we need to clean it up. And I decided to clean it using this replace outlier based on distance function. So this function pretty much takes an distance threshold. So this is the allowed movement of ball between detections, and if the ball moved more than that allowed distance, I just discard that detection. And turns out this works really well. If we run this function on our path, and I set the max distance to be 5 meters. I think it's more than enough. The path we got is actually really clean. We covered a lot so far, but before we wrap it up, let's discuss some important considerations that make or break your football AI project. Our models have been fine-tuned on broadcast footage captured from above with good view on entire pitch. Significantly different perspectives, such as low-angle shots or those from behind the goal, may lead to unexpected behavior due to changes in object appearance and scale. In such cases, it will be necessary to expand our datasets with images taken from those new perspectives and retrain the model. Moreover, when the camera is low or players clustered tightly, occlusions become more frequent. Those can easily disrupt our ByteTrack tracking algorithm. It might be necessary to apply re-identification mechanisms or trackers that consider object appearance, such as massa. While homography effectively maps ground-level objects to 2D pitch representation, it struggles with objects in the air. This is most notable with long passes or high shots, where the ball trajectory appears curved on a radar view instead of true straight line. Addressing this may require incorporating 3D ball tracking or trajectory estimation models. The overall quality of our perspective transformation hinges entirely on the accuracy of our keypoint detector. Even minor errors in landmark localization can lead to skewed player position or distorted pitch visualizations. One of the tactics we applied to solve this problem was averaging out our homography matrix across time window, but depending on the specific case, we may need to come up with more robust strategy. Last but not least, for live applications, the entire AI pipeline will need to run efficiently to keep up with game space. The proposed solution is only proof of concept, and we are currently running at around 1 frame per second, far from required 30 FPS. To apply this approach on live sport events, it will be necessary to optimize all models by choosing smaller architectures or using advanced strategies like quantization to speed up the inference. Today's project barely scratched the surface of AI in sports analytics. We tackled key challenges like player tracking and perspective transformation, but there is still so much more to explore. From advanced player metrics to model that predicts what will happen next on football field. Leave your questions and ideas in comments below and join me for upcoming community session where we will talk more about this project and sport analytics in general. I'm curious if you have any ideas how to apply strategies we explored today to solve problems outside of sports. If you enjoyed the video, make sure to like and subscribe and stay tuned for more computer vision content coming to this channel soon. My name is Peter and I see you next time. Bye.